Hello, everyone. Today, He Guo is going to from Wumeo University is going to tell us about the intersections of a matroid.
Okay, thanks a lot for the invitation and the introduction. Today I will tell you some results based on joint work with Ron Aharoni, Eli Berger, and Daniel Kotlar from Israel. And feel free to interrupt me if you have any question during the talk. So it's okay if you do not know anything about matroid before. I will give you the basic definition. So we start with the hypergraph. So we know that the hypergraph is on our vertex set V, and the edges are just the collection of subset of the vertex set. So in this talk, we assume that our hypergraph does not have isolated vertices. It means for any vertex, it is contained in some edge. The hypergraph is called K-uniform if each edge of the hypergraph has size K, and it is K-partite if you can divide the vertex site into K parts such that each edge intersects with each part at once. And we use this notation H induced on U, where U is a subset of U vertex of V, as the induced subhypergraph, which means you take all the edges that completely contained in U. So that's the induced subhypergraph. And we also didn't define the rank of our vertex site. It's just to be the maximum size of an edge in the induced subhypergraph. And we also define the rank of hypergraph. It's just to be the maximum rank, maximum size of an edge in U hypergraph. So that is equal to the rank of the whole vertex set V. Okay, so that is the definition of hypergraph. And then we can move on to a special class of hypergraph, which is we call abstract simplicial complexes. And we also just call it complex. So a hypergraph C is a complex if it is closed down under taking subset, which means if you have an edge F that is contained in U hypergraph C, then for any subset of UF, if you have an edge E is contained in U hypergraph C, then for any subset of edge, it's also contained in C. Okay, so I see someone raise hand. So is there a question about this definition?
Sorry, can I just ask a question about what you meant by K-uniform? That binomial coefficient type of notation. What is that set or family of sets?
It means any set in U hypergraph H has size equal to K.
Got it. Thank you so much. That was my question.
Yeah. All right. And okay, so we have the complex, that is the hypergraph whose edges are closed down under taking subsets. And here are some examples about the complex. One is called the independence complex, which means for a graph G, the complex IG, the independence complex IG is just a collection of all the independent sets in G, where our vertex site is called an independent set in G if it does not contain any edge of G. So you can check that if you have an independent site, then any subset of your independent set is also independent. Therefore, the independence complex is really a complex. And similarly, for a graph G, we can also define the matching complex on the edge side of G, which means that is a collection of all the matchings in G. So edge side is a matching if any two edges in your edge side, they do not touch each other. They do not intersect with each other at the vertex. So you can also check that any subset of a matching is a matching. Therefore, the matching complex is really a complex. So here are two basic examples about complex. Okay, so I think it's clear. Then we can give the formal definition of matroid, the main topic of this talk, because matroid is some special complex, which means if M is a matroid, then first it's a complex, which means it's closed undertaking subset. We do not want M to be trivial, so we just assume that M is non-empty, which means the empty set is an edge set of M. And furthermore, I'm also satisfy one more condition, which is called the independence augmenting property, which means if you have two edges or two sides in your M, in your matroid M, and one is of size less than the other, then you can pick one vertex or one element from the larger size side T minus I such that if you add that element V into the smaller side, what you get is still a side in your M. So that is called the independence augmenting property. And I will give you an example to explain why such property is called the independence augmenting property. So first we can check that if you have a matroid M, then any non-empty induced subset, some matroid, it is also a matroid. You can check it that it satisfies this augmenting property. One more example about the matroid is the following example. So the following example is that if we consider the collection of the sets of independent, linearly independent vectors in some finite dimensional vector space, then we can see that this collection form a matroid. So we can check them one by one. So if you have a set of linearly independent vectors, then any subset of it is still linearly independent. And the independence augmenting property is that if you have two set of linearly independent vectors, S and T, then you know there must exist some vector in the larger dimensional subspace, which is not in the smaller side, such that the union of them are still linearly independent. So that is why this property is called the independence augmenting property, because from a smaller linearly independent side, you can add one more element from a larger one to get a larger independent side. So here is an example from the linear algebra. And of course, we have some example from set theory. That is the following example, which we call the partition matroid. So assume you have a set V, and the partition matroid is defined as the following. So first, you can divide the vertex at V into some parts, some disjoint part, say V1 up to VA. And a side is in the partition matroid if and only if this side intersect with each part at most once. So you can check that all such set I's satisfies the closed down property, and it also satisfies the augmenting property. So if you have set T, which has s greater than I's, then you know that T must intersect at some part which S does not intersect. So you can add that element into S to form a larger set, which is still satisfy this intersection property. So that is called the partition matroid. And you can generalize the definition of partition matroid to get the generalized partition matroid, which means this time you also divided the vertex the set V into some parts. This time, you do not just require the intersection to be set at most one, but you can assign some numbers, say P1 up to PA, such that the intersection of each part is at most PI. So that is called the generalized partition matroid, and you can also check that it satisfies the definition of matroids. Okay, so here are the definition of matroids. Is there any question about this definition?
Actually, could I ask a question?
Sure.
Are the elements of these families of sets partitions? I guess I didn't catch that. Are they? Of the, do you know what I'm asking?
So you can assume that this V is because we know that a matroid is also a hypergraph. So you can assume that this V is your vertex set. And if you can find a partition such that you partition this vertex site into disjoint parts, say V1 up to VA, and you want to know how does the edge look like. The edge just intersect each part at most once. So that is the edge of your partition matrix P.
Okay, I guess I'm following you. Okay.
Okay. All right. Is there any other question about the definition? All right, now let's move on. So here we know that the matroid is some special complex. And the natural question to ask is that because a matroid is a complex, but a complex is not necessarily a matroid. A natural question to ask is that can we write a complex as intersection of some matroids? So why we have such questions? So here is a basic example that we can write this kind of complex as intersection of two matroids, actually two partition matrix. Let me tell you this example. So if you have a bipartite graph G, and you have two sides X and Y, and as we have seen, the matching complex of G is complex. And actually, you can write this complex as intersection of two partition matrices. Let me show you a picture. So assume this is your graph G. And you want to write the matching complex of this graph G as intersection of two partition matrices. So the first partition matrix, which we named M, are just all the stars at whose parts are just all the stars at each vertex in the first side. So for example, this purple edge is a star as x1. The two green edges form a star as at x2, and so on and so forth. So they form the parts of your partition matrix. On the edge of your matrix can just touch each star at most once. So that is your first partition matrix. On the second partition matrix, whose parts are the star at the second size. So which means the first part is just the star at Y1, which are the blue edges, and second star are the teal edges, and so on. And then you can see that if you have a matching, then it touch each star at most once. It touch each vertex at most once. Therefore, it's in the first partition matrix, and it's also in the second partition matrix if you look at the second part. So that's how you write a matching complex as the intersection of two partition matrices. And on the other way around, if you have two partition matrices on the same ground side, you can also define a graph G such that the matching complex of G is just the intersection of the two partition matrices. That is a quick exercise. So that's why we ask the question that can we write a complex as intersection of matrices? And actually, the answer is yes. We prove that if you have any complex on n vertex side, then we can write it as the intersection of at most say 2 to the n matrices. We can even write it as the intersection of 2 to the n generalized partition matrix. And one thing I would like to see here is that this exponentially many is not too bad, because we also find an example such that complex, if you want to write it as the intersection of some matrices, then you need at least n choose n over 2 many matrix, which is also exponential. So that is the first result I want to tell you. And then I will move on to the some coloring problem of matroid. So before moving to the coloring problem of matroid, so first let me remind you the chromatic number of a graph G, which you might be more familiar with. So recall that if you have a graph G, then the chromatic number of the graph G is the middle number of infant set G, such that the union of those infant set is just equal to the vertex set of G. And equivalently, it means it is the middle number you need to color the vertex of G, such that any two color receive the same color is not adjacent to each other. Okay, so that's the chromatic number of graph G. And people also study the least chromatic number of a graph G. So this time the least chromatic number is the mean number K, such that you assign a list for each vertex. And the list is of size K. And so that you can choose a color from each list of each vertex, such that the vertex has the same color for my infant side. So that is the least chromatic number of G. So you can see that the chromatic number is just a special case for the least chromatic number, because in the chromatic number, all the lists you assign to different vertices, they are the same. They have the same color. But for the least chromatic number, those lists can be different for different vertices. So that's why you can see that the chromatic number is trivial lower bound of the least chromatic number. Naturally, this strictly inequality can hold. And as an example, I can tell you that the least chromatic number of the complete bipartite graph K33 is strictly greater than 2. Because K33 is a bipartite graph, you know the chromatic number is 2, but the least chromatic number is strictly greater than 2. And here is the short proof. So assume this is your K33, and the list you assign to this vertex is 1 and 2, this 1 and 3, this 2 and 3. They are just all the subset of 3 choose 2, similarly for the other side. The first observation is that if you want to choose one color from the list in this side, then you need to have at least 2 colors to be chosen for the first side, because see if all of them receive the same color 1, but 1 does not show up in this list, so you cannot choose 1 from this list. Therefore, you need at least 2 colors to be chosen from this part. Say you choose 1 and 2, maybe you choose 1 for this, 1 for this, and 2 from here. But it will cause a problem. So if you have 1 and 2, then you consider this vertex, because all the colors in its list are 1 and 2. You cannot choose neither 1 or 2 that is not adjacent to 1 or 2. So it will cause a problem. So it means if the size of the list, color list is just a 2, then it's not enough for you to find the proper list coloring. So that's why the list chromatic number of K33 is strictly greater than 2. You can generalize this example to show that the list chromatic number of KNN is strictly greater than N, where N is equal to this number. And the idea is similar. For each of these vertex, the list is just all this 2k minus 1 choose k set. And by a similar argument, you can show that the list chromatic number of KNN is strictly greater than k. But we know that the bipartite graph KNN, the chromatic number is just a 2. So it means the ratio between this list chromatic number and the chromatic number can be arbitrarily large. Okay, so that is the chromatic number and the list chromatic number for graphs. So is there any question about this part? All right, so if not, we can move on to the definition for involving matroids. And yeah, it's actually for the complex. So similarly, we can define the chromatic number for a complex. So the chromatic number of a complex C is just the mean number of the set in C, such that the union of the set is equal to the vertex of C. So previously, recall that for chromatic number of a graph, that is a special complex C, where you take C to be the impedance complex of your graph G. And this is the definition for chromatic number. And Edmonds in 1965, he proves that for a matroid M, the chromatic number of your matroid is just equal to this number, which we denote by delta rank of M. The definition of delta rank M is just the maximum over all the subset, such that the size of S divided by the rank of your S. So first at least we can see this trivial lower bound of the chromatic number of M, because if you find a mean number of sites in your matroid whose union is all the vertex out of your matroid, then if you induce on the set S for any set S, to cover all the set of S, because you know the maximum size of H in your induced subhypergraph is this rank. Therefore, you need at least S divided by this rank many edges to cover the vertex set. Therefore, we can see that this maximum delta Rm is trivial lower bound of delta M. But Edmonds shows that actually the equality holds. And similarly, we can generalize the least chromatic number for a graph to the least chromatic number of a complex. And here is the definition. So the least chromatic number of a complex C is just the minimum K, such that if you assign a list of colors, each of the list is of size K, then you are able to choose a color from each list of each vertex, such that the vertex you color by the same color is edge of the complex C. Okay. So again, in the last example, the list chromatic number of a graph, there the C you choose, there the C you have is just the impedance convex of graph G. The SIMO in 1998 proves that for matroid I, the least chromatic number is just equal to the chromatic number of a matroid, not like the graph case, because as we have seen in the graph case, the strictly inequality can hold. Okay, so here is some result about the chromatic number and least chromatic number of matroid. So is there any question?
Yeah. So if we're thinking of the complex as coming from a hypergraph, is this sort of like the opposite of regular chromatic number? Because here it looks like we're saying that
Yeah, here is more like the
go ahead.
here because here is more like you cover the vertex set by the edge of C, if you will, the set in you see as an edge.
So every edge should be monochromatic, is like all the vertices within that edge. Is that what that second bullet point is saying? Is that?
Yeah, so if you consider this chromatic number, so it means the vertex in an edge are monochromatic. Yes.
Okay, thank you.
Yeah. Yeah, it's a good point to distinguish the difference here. Okay, so next we can move on to our result. So first, because here we have very good understanding of the chromatic number and the least chromatic number of a matroid. So the next step to understand is what if you have the intersection of two matroids? And here is a conjecture by Aharoni and Berger. The conjecture that if you have two matroids, M and N on the same ground side, then the chromatic number of the intersection of them is at most the maximum of this one and this one plus one. So let me tell you that this upper bound is not too far from the trivial lower bound. So here is a trivial lower bound. So because if you can choose some common edges from M and N to cover the vertex set here, then because it's common edge, then it is also from M or from N. So it's also, so it means the chromatic number here is at least the maximum of, is at least each of them. Therefore, this is a trivial lower bound, and you can see the difference is just one. And there is some example showing that the strictly inequality can hold here. So it's really not far from the lower bound. And what is the known? Here are some known results about this conjecture. So first is the conic edge coloring theorem, which you might have studied in your graph theory course. So it says that for any two partition matrices and M and N on the same ground side, the equality holds here, which means the chromatic number of their intersection is equal to the maximum of each of them. So because at the beginning we have seen that the intersection of two partition matrices is just the matching complex of a bipartite graph. And you can see that the chromatic number of the intersection is just the edge coloring number of the bipartite graph. And the conic edge coloring theorem says that the edge coloring number is equal to the maximum degree of your bipartite graph. And you can see that actually this one is equal to the maximum degree because the Edmonds theorem, where this one is really to the maximum degree because the chi-m is a partition matrix. You can find that is equal to the maximum size of a part, which is a star, and that is the maximum degree. Okay, so that is a conic edge coloring theorem. And here we prove that not just for partition matrix. So if you have two generalized partition matrices, then the chromatic number of their intersection is also equal to the maximum of them. Another result about Aharoni and Berger is that if you have two arbitrary matrices at M and N, then the chromatic number of their intersection is at most twice as the maximum of each of them. So recently we improved this result by showing that if you have any two matrices and M and N, then the least chromatic number of them is at most not 2 times the maximum of them, but just the sum of them. So recall that this least chromatic number is an upper bound of the chromatic number. So we improve this result a little bit. So that is about the chromatic number, conjecture and result about the chromatic number. And there are also conjecture about the least chromatic number. So by Kiraly and Berczi-Schwarcz and Yamaguchi, they conjecture that if you have any two matrices and M and N, then the least chromatic number of their intersection is equal to the chromatic number of the intersection of them. And regarding this conjecture, there are some known results. So the first one is by Gowen in 1995. It proves that any two partition matrices M and N on the same ground side, the least chromatic number of their intersection is equal to the chromatic number. So again, if you use the correspondence, it says that the least edge chromatic number of a bipartite graph is equal to the edge chromatic number of the bipartite graph. So that is a Gowen's result. And we extended it to the case side, not just a two partition matrix, but two generalized partition matrix. And another conjecture by this group of people is that perhaps they asked for some weaker results, is that the conjecture that there exists some constant L such that the least chromatic number of the intersection of two matrices is at most L times the chromatic number. And we actually prove this conjecture by showing that not just for the intersection of two matrices, but if you have an intersection of arbitrarily K matrices, then the least chromatic number of the intersection is at most K times the chromatic number of the intersection. So as you can see in the case that K equal to 2, you can take the constant L to be 2. Okay, so here are some conjecture and the results in this area. So is there any question? All right, so if not, I will move on to discuss a little bit about the proof of this result. So before giving the proof of this result, let me give you one more definition from the topology, algebraic topology. So if you have compact C, so we can define the homotopic connectivity of the C to be the minimal dimension of a hole in your compact C. So it doesn't matter if you do not understand what is a hole. So if you want some formal definition, it means that if you have simplicial map of the K-1 sphere into your S, that cannot continually extend to the K disk into complex C. So here are some examples. So if your complex C is empty, if and only if the connectivity is 0. And the connectivity is equal to 1 if and only if your complex C is not non-empty and is not path connected. So you can check that if it's not path connected, then you can take one vertex from one component and another vertex from the other component. And because you know S0 is just 2 points, you map this point to this point and the other point to this point. You cannot extend to B1, which is a line segment into S. So that's why the connectivity of this one is equal to 1. And another example is the connectivity of, if you have some set V, then if your complex is all the subset of V, then it is contractible, therefore the connectivity is equal to infinity. But if you remove the largest phase, the maximal phase of your power side, then you know the maximal phase, it forms a hole. Therefore the connectivity will just be the dimension of the largest hole, which is of dimension the size of V minus 1. So here are some. It's enough to just know the connectivity of such examples. And if you want some more formal definition, there is another formal definition which we call the homological connectivity of complex. It is just a minimal K such that its K minus 1s a reduced homological group is not non-zero. So that is more algebraic flavor definition. And the He-Guo theorem says that they're almost one is greater than the other one, and the equality holds in most cases. Okay, so and one more definition is the join operation, which we call the join of two complex. So if you have a complex C and you have complex D, we define the join of them, and we denote it by the C star D, just to be on the, you make the vertex of C and D disjoint, and H is in the join if and only if it has this form. So it's a union of an H in UC with an HT in the complex D. So that's a join of two complexes. And the connectivity satisfies sub activity property, which means if you have a join of two complexes, then the connectivity of the join of them is at least the sum of each of them, the connectivity of each of them. So that will be enough for us to prove our main result. Okay, and another ingredient is topological Hall theorem. So what is topological Hall theorem? So first, let me remind you what is Hall theorem in graph theory. And I'm sure you have studied this in your graph theory course. So the Hall theorem says that if you have a bipartite graph G, and the two sides are just X and Y, then there is a matching from X to Y if and only if for all the subset of you X, the size of the neighbor of you set I is at least the size of your I. So that you can easily see that it's a necessary condition, because if you have matching, then I must match to the same number of vertices. So that's why you have at least here. So that is the Hall theorem. We can also define a similar thing in a complex, which we call, that is a counterpart of matching, which we call the D-transversal So what is D transversal? So assume you have a complex D and you have a collection of vertex subset of your complex D. Then D transversal is just a choice function such that you choose one vertex from each vertex side. And it satisfies that all the vertices you choose form an element in your D. So that is a D transversal. And it is natural to study when does a D transversal exist. So that is the so-called topological house theorem, which is found by Aharoni and He Guo. So they prove that if you have a complex D and you have a collection or subset of your vertex at D, then a sufficient condition for D transversal to exist is that for any subset of your index set, if you take union of your vertex subset on this index set and D induce on them, then the connectivity should be at least the size of your index set. So if this condition hold, then the topological host theorem proves that there exists a D transversal. Okay, so that is a main tool for us to prove the least chromatic number result. So is there any question about this topological whole theorem? All right, then we get all the result we need to prove the main result. So recall that we want to prove that the least chromatic number of intersection of K matrices to be at most K times the chromatic number of intersection of K matrices. And again, we can find a trivial lower bound on the chromatic number of a complex C. We have seen this before in the advanced result. Recall that we denote this delta R to be the maximum over all the vertex subset S, such that S divided by the rank of your complex on your vertex set S. Because to cover all the S, we need at least so many edges in your sub-hypergraph to cover S. Therefore, this is a trivial lower bound. And similarly, we can define this connectivity maximum degree delta eta C to be the maximum over all the subset S, that is the size of S divided by the connectivity of your complex induced on your S. So that is the definition of delta eta. And Aharoni and Berger proves that if you C is the intersection of K matrices, then the connectivity of C is at least the rank of C, which is the largest common edges of your K matrix divided by K. And with this in hand, so assume our complex C is the intersection of K matrix, and assume on A, on the vertex set subset A, you attain the maximality of delta eta. Then by definition, we know that this delta eta is just the size of A divided by the connectivity of C induced on A. And then we apply this Aharoni and Berger result. Because this eta is greater than this one, therefore we can replace this eta by the rank of C induced on A divided by K. And therefore we find that size of A divided by the rank of C on A is at most this delta rank R, which is K times delta rank of R. And together with this trivial upper bound, we know that this is at most K times chromatic number of C. So therefore, to prove the least chromatic number is at most K times the chromatic number, it remains to prove that the least chromatic number of C is at most the ceiling of this delta eta. So if we have the least chromatic number here, then we will prove everything. So what remains to prove is that for any complex C, we want to prove the least chromatic number is at most the delta eta of C. So that will be enough. So what we should prove is that if we have a list of color for each vertex, which of size exactly equal to the ceiling of delta eta, then we should be able to choose one color from the list of each vertex, such that all the vertex receive the same color. They are in C. So that is our goal. And for this purpose, I will show you a picture about this proof to show that the least chromatic number of C is at most the delta eta of C. So here is a picture. So let's skip this. Here is a picture. So assume here are the vertices of U complex C, CV1 up to V4. And each vertex receives some color. For example, this vertex V1 receive color 1, color 2, and color 3. This vertex 2, the color list are just color 1, color 2, and color 4, and so on and so forth. So assume V1 receive the color C1 is in the list of V1, then we make a copy of V1 here. And a copy here, in the C1 layer, and so on and so forth. And therefore, for each vertex VL, we make so many copies because the size of list is this one. So we make so many copies, and we denote the size of these copies by VV1, and similarly for VV2 and VV3. And we define a new complex, which we call D. How do we make D? So first of all, the layer of C1, that is all the vertices receive such that the C1 is in their color list. We make the complex C induced on this vertex side on these copies. So that is the C induced on all the vertices, so that the color C1 is in their color list, and so on. We can make another complex here. We make the join of them. That is our D. So our D the vertex set are defined on all such copies. And then we can apply the topological Hall theorem to find the D transversal. So if we have a D transversal, so that each subset of the vertex D is just all the copies of a vertex here. So it means, so here is one subset of VD, here's another subset, here's another subset, here's another subset. So we will those vertex vertically. And if we can choose one vertex from each subset, say we choose this one, this one, this one, this one. If they are in D, because that D is the join of them, it means in each layer, if we wheel them horizontally, it means in each layer they form a set in UC, and that will be done, right? So what we need to show is we need to show this complex D satisfies the topological Hall theorem. That is what we want to prove here. So we need to show that the connectivity of any, the union of any index is at least the size of index. We can show it because for any subset, for any index at I, The union of them, by definition, they are just the join of the complex here, the complex in C. And by the subactivity of the connectivities, we know this one is at least the sum of the connectivity here. And then by the definition of the delta eta, we know that delta eta is at least the size of this side divided by the connectivity of them. Therefore, we have this lower bound. And the last thing to show is that is this inequality hold, and that is actually by a double counting argument. Recall that for any set I and any vertex here, it has delta eta copy of them. So if you count it vertically, the sum of this one is just the number of the vertices, which is the size of I times, because each of them has so many copies, and you have this term. And then you divide by this term, which is exactly equal to I. And we have checked that this complex D satisfies the topological Hall condition. Then we can find a D transversal, which is exactly the least coloring we look for. Therefore, we prove that the least chromatic number of C is at most the delta eta of C. Is there any question about this proof? All right, so if not, we can make a summary of this talk. So in this talk, we introduce the definition of chromatic number of a complex C, which is the minimum number of sites in C whose union is the vertex of C. And we also define the least chromatic number of a complex C, which means you give each vertex a list of colors, and the list is of size K. Then you are able to choose one color from the list of each vertex so that all the vertices receive the same color is an element in UC. And we prove that if your complex C is the intersection of K matrices, then the least chromatic number of your complex is at most K times the chromatic number of complex C. The proof is by applying the topological Hall theorem. And it also saves some conjecture by Kiraly and Berczi. Let me stop here. Thank you. Is there any question?
Thank you for the nice talk. How some of them might be a silly question. You were talking about the join of a matroid. Is it the chrome? Do people study the chromatic number of the join, or the least chromatic number?
Mm-hmm.
I mean, are there some result about this?
So you mean the join of some complex?
Yeah, maybe complex. I don't remember.
Okay.
Is it still complex? It might be a silly question.
Yeah. At least some true bound will be if the join of them, then it's a maximum of each of them.
Yeah.
Yeah, at least yes. Maybe the join is, if you understand what happens at each part, because the join is just the vertex disjoint of each copies. If you understand what happens in one copy, then you understand what happens for the join of them.
Right. Thank you.
Yeah, so that's why people want to understand what happens about the intersection, because they are on the same ground side.
Right.
And you try to influence each other.